Hey everyone, welcome back to my YouTube channel Act 1. The anomaly. Look up into the night sky. What do you see? A familiar companion, a radiant orb that has guided sailors, inspired poets, and illuminated our darkest hours for millennia. It is the moon, our closest celestial neighbor, a constant presence in humanity's story. Yet, despite its familiarity, the moon harbors one of the most profound mysteries in all of astronomy: its very origin. How did this colossal sphere come to orbit our planet? Where did it come from? The answers, as we are about to discover, point to a cosmic catastrophe, a collision of worlds, and the ghost of a lost planet named Theia. The moon is no ordinary satellite. It is a true anomaly in our solar system. Consider its size. Our moon is remarkably large compared to its parent planet. Earth's diameter is about 12,742 kilometers, while the moon's is approximately 3,474 kilometers, making it more than a quarter the size of Earth. This ratio is far greater than that of most other planets and their moons. For instance, Jupiter's largest moon, Ganymede, is only about 1/25 the size of Jupiter. This sheer scale immediately sets our moon apart, suggesting a formation event far more dramatic than the gentle accretion of dust and gas that typically forms smaller satellites. Beyond its size, the moon presents other perplexing characteristics. Its density, for example, is significantly lower than Earth's. While Earth has a dense iron-nickel core, the moon's core is much smaller and less dense, indicating a different internal composition. This suggests that the moon is largely made of lighter, rocky material, rather than the heavy metals that dominate Earth's interior. Then there's its orbit. The moon's orbit is tilted by about 5 degrees relative to Earth's orbital plane around the sun, a subtle but significant detail that challenges simple formation scenarios. If it had simply condensed from the same cloud of material that formed Earth, we might expect a more aligned orbit. For centuries, these peculiarities fueled speculation. How could such a massive, low-density body, with its unique orbital dynamics, have come into being? Was it a captured rogue planet? Did it spin off from a rapidly rotating Earth? Or did it form alongside Earth, a twin born of the same cosmic dust? Each traditional explanation, when scrutinized against the growing body of evidence, crumbled, leaving scientists scratching their heads. The moon, in its silent vigil, held its secrets close, defying easy answers. But the universe, in its grand design, often leaves clues, subtle whispers of past events embedded in the very fabric of celestial bodies. And it was by meticulously collecting these whispers, through the lens of telescopes and the analysis of moon rocks, that humanity began to piece together a truly astonishing story. A tale of a cosmic impact, a cataclysmic birth, and the lingering shadow of Earth's lost sister planet, Theia. Act 2. The first clues. Asterisk. For much of history, the moon's origin was a subject of philosophical debate and wild conjecture. As scientific inquiry advanced, 3 primary hypotheses emerged to explain our moon's existence, each attempting to reconcile the observed facts with the laws of physics. The first was the fission theory, championed by astronomer George Darwin, son of Charles Darwin, in the late 19th century. This theory proposed that the early Earth was spinning so rapidly that a bulge formed, eventually tearing away to become the moon, much like a blob of clay flung from a potter's wheel. Opponents pointed to the Pacific Ocean basin as a potential scar left by this dramatic separation. However, calculations quickly showed that Earth would have needed to spin impossibly fast for such an event to occur, and the physics simply didn't add up. There wasn't enough angular momentum in the Earth-Moon system to support this idea. The second major theory was the capture theory. This hypothesis suggested that the moon formed elsewhere in the solar system and was later gravitationally snared by Earth as it passed too close. This could potentially explain the moon's distinct composition and orbital tilt. But capturing such a large body into a stable orbit without a catastrophic collision is incredibly difficult from a gravitational mechanics perspective. The odds of such a precise capture, without the moon either crashing into Earth or slingshotting away, are astronomically low. Furthermore, the capture process would likely have resulted in a highly elliptical and irregular orbit, not the relatively stable, near-circular path we observe today. The third theory, coformation or condensation theory, posited that the Earth and Moon formed simultaneously from the same swirling cloud of gas and dust, much like a binary planet system. In this scenario, the Moon would have accreted in orbit around the nascent Earth. This theory could explain the Moon's proximity to Earth, but it struggled to account for the Moon's lower density and its relative lack of iron compared to Earth. If they formed from the same primordial material, their compositions should be far more similar, particularly in terms of metallic content. Also, it didn't easily explain the angular momentum of the Earth-Moon system. By the mid-20th century, these traditional theories were facing significant challenges. The scientific community was in search of a more robust explanation. The turning point arrived in the 1970s, largely thanks to the insights of 2 planetary scientists, William Hartmann and Donald Davis. In 1975, they published a paper proposing what would become known as the giant impact hypothesis. Their radical idea was that the moon formed from the debris ejected after a massive, Mars-sized protoplanet collided with the early Earth. This theory offered elegant solutions to many of the long-standing puzzles. The impact would have generated enormous heat, vaporizing volatile elements and explaining their scarcity on the moon. The ejected material, largely derived from the outer, rocky mantles of both colliding bodies, would explain the moon's lower density and lack of a large iron core. The sheer energy of the impact would also impart the necessary angular momentum to the Earth-Moon system, accounting for its